Okay, I know we didn't finish this last problem in the last class, so I just wanted to finish it up. When we actually come in here and factor this quadratic, we end up finding that x could be 14 or x could be 2. And then we take both of those values of x and plug them back into our equations. And you do end up seeing that you have the point 2 comma 5 and the point 14 comma -1. Now, if I plug both of these in, and you can do this for any of your solutions, whether you're solving a system of equations with just lines or when you're doing these nonlinear systems, you can plug your values of x and y back into both the equations to see if they work. And so if I plug them back into the line, I have, well, our y value here is -1. So you want to see, does -1 equal -1/2 times 14 plus 6? So does -1 equal -7 plus 6? And it does. That's valid. So let's try the other problem. So if we have -1, does it equal the square root of 14 plus 2 plus 3? And 14 plus 2 is 16, and the square root of 16 is 4. And here we see that this is not going to work. This is not valid, which means that this answer right here is extraneous. And we could double check our point 2 comma 5. We could plug it into both equations. Oops, our y value is 5. And if we have -1/2 times our x value of 2 plus 6 and 5, does it equal -1 plus 6? And that is valid. Now let's try the other equation, the radical equation. So we want to see if -1 does equal the square root of, I'm sorry, I keep on pulling in the wrong y value. 5, does 5 equal 2 plus 2 plus 3? Well, 2 plus 2 gives us 4, and the square root of 4 is just 2, so we have 2 plus 3, which does, in fact, equal 5. So our answer here is that point at 2 comma 5, which we saw when we graphed this. So we worked all of these out, finding those solutions or those intersection points algebraically using our square root function, our absolute value function, or our quadratic function. So now what I want to do is going to move on and take a look at how we can find a system of equation and intersection points between a line and a circle. So remember, when we are talking about a circle, as I've got listed and written right here, our equation of a circle is x minus h squared plus y minus k squared equals r squared. And that's where r is going to be our radius, and our center is at h comma k. So let's take a look at some examples. If we look at this graph over here to the left, we see on our circle, our center is at 0, 0. So our center is at 0, 0. And if we count from there, we can figure out what our radius is. And it looks like our radius is going to be 3. So if we're writing the equation of the circle, it's just going to be x squared plus y squared, and it's going to equal our radius squared, so 3 squared, which is 9. And then if I want to go over and write the equation of the line right there, we see that our y-intercept is down at -3. And if we count our slope, we can go up 2 and to the left 1. So our slope is going to be up 2 and to the left 1. So our slope is just -2. So we can just put that information in slope-intercept form, y equals mx plus b. And so the equation of that line is going to be y equals -2x minus 3. Now, if we look at this particular graph, we see that there are two separate intersection points of the line and the circle. We see one of them here is pretty easy to pull off the graph. And so before I get there, these are just two solutions or two intersection points. So we can see that one of them is at 0 comma -3, but this other one, it's not an integer, so we can't exactly tell where that is. And so this is a situation where we would want to use algebra to figure out what our intersection points are between these two equations that I've got, that I have squared over here or boxed in. I'm highlighting them right now in yellow. So we can use substitution here to be able to solve for our intersection point. So I'm going to plug in this negative 2x minus 3 in for y in my circle equation. So I have x squared plus negative 2x minus 3 squared equals 9. Now when I FOIL minus 2x minus 3, I'm going to end up getting 4x squared plus 12x plus 9 equals 9. And so now I've got all x's in my equation. And I'm just going to combine like terms. I do see that I have a 9 on both sides of the equation, and so those are going to cancel each other out. And I've got 5x squared plus 12x equals 0. And now I just need to factor this. Here it's not a trinomial, it's not a difference of two squares. So really I'm just factoring out a GCF, which in this case is just x. So we have x times 5x plus 12 equals 0. And I can set each one of those equal to 0. I can say x equals 0 and then 5x plus 12 equals 0. And if I solve this equation right here, I'm going to get x is going to be negative 12 over 5. So just like we've done before, when I find my x values, now I'm just going to plug them back in, and I can plug them back into either of my equations to see if they work. Well, it's probably easier to plug them back into my line, so I'm going to do that. If we plug it back into our line, we have y equals negative 2 times 0 minus 3. Well, this first term is going to end up being 0, so we have y equals negative 3, which gives us that point that we can see on the graph that's at 0, negative 3. Now, if I put negative 12/5 into my equation, I have y equals negative 2 times negative 12/5 minus 3. Now, I'm going to have to get a common denominator to combine these terms together. I'm first going to multiply here, and I get 24/5. And when I get a common denominator, this is going to end up being 15/5. So 24/5 minus 15/5 is going to give me 9/5. So my other point over here is negative 12/5, 9/5. And so now we have our two separate equations to see what is going on here to figure out our intersection points between the circle and the line. Now, one thing I do want to show you, if you had chosen here to plug x equals 0 into the circle equation, you would have had 0 squared plus y squared equals 9. And so y squared equals 9, and when you take the square root out of both sides, you end up getting y equals plus or minus 3. Now, if we look at this, we would see here that 3 is actually an extraneous solution, because if we ended up plugging that into the line, it would not work. So we do have to throw out 3 as being a possible value for y. So you always want to be able to double check what your answers are going to be there. Okay, so let's keep moving on. So this next question says, can a circle and a line have no solution? And let's think about that for a moment. If it has no solution, is there an intersection point? So I want you to think about that and pause the video and come up with an example and see if you can write an example for each of the things that you come up with, the line and the circle, and come back and check your answer against what I've come up with. So your circle and your line probably look a little bit different. They may not be exactly the same, but you want to make sure that your circle and your line do not touch or intersect at any point, and that this is when you would have no solution. And you see that I've written my equation of my circle using my center and my radius that I had graphed, and then I also have my equation of my line using my slope and my y-intercept. So then the next situation that we want to think about is, could a circle and a line only have one solution? So I want you to think back to your geometry days last year and think about when a line and a circle could only intersect at one point. So think about that, pause it, talk with a friend, and draw an example, and then come back and take a look. So I ended up using the same circle that I did in the previous example, where the center's at 3, 4, and it's got a radius of 5. And I just drew a vertical line that touched the circle there at x equals -2. Actually, the intersection point is at -2, 4. So we have talked about finding solutions with lines and several other functions. We talked about a quadratic function. We didn't have an example with a cubic, but you could do that as well. Absolute value and a square root, and we just showed how to do a circle. So what I would recommend doing now is I want you all to work through these practice problems, and you can, if you want to pause it and come back, you can listen to my explanation, or you can stop the video and just take a look at the answers in the content library. Okay, so I graphed my square root function here, and I also graphed my line. And from my graph, I can see that the intersection point is at 6, 1, and we're only going to have one solution. Now, when I solved it algebraically, one thing I do want to point out, I didn't want to have to deal with foiling something with a fraction. So I ended up multiplying the entire equation. I ended up doing it by -2. So I had a positive x value there. And it made it easier for foiling when I had x minus 18 in parentheses squared. You do notice when I have this -6 times the square root of x minus 2 in parentheses squared, I square the -6, which gives me 36. And then the square root of x minus 2 squared just gives me x minus 2. So I went through and solved for x, and I did get another value of x out at 66. But I know even if I go way out here to 66, that's an extraneous solution. And I could check that by going and plugging that value, x equals 66, into both equations to see if it is extraneous, or to verify that it's extraneous. So I had the point x equals 6, and I just plugged it into my line equation to get the y value of 1. So that intersection point is at 6, 1. Now my next equation, we did have an absolute value and a line, and so I graphed both of those and found that I actually had two different intersection points, one at -5, 2, and one at -2, 6. And so then I just did my algebra work to isolate my absolute value. I did have to divide both sides by 3. I needed to completely isolate that absolute value before I created my two equations right here. And then I had just to work to solve for x. And once I found my value of x, I could just plug that into one of the original equations to solve for y to get my two separate intersection points. So this last problem is just solving the system of equations using elimination. And what I did here, I decided to get my y terms on one side of the equation and then get my x terms on one side of the equation, including the x squared. And then I just added my two equations together. My y's canceled out. I got 6x minus y squared equals 5. And then I just brought it all over to the right-hand side of the equation just so my x squared term would be positive. And I factored it and used my two values of x to plug back into one of the original equations to solve for my value of y.